Today's lesson is section 1.2, Functions and Their Properties. This section is a two-part lesson. Today we'll be going over part 1. The first thing we are going to discuss is the definition of a function. Now, the book's definition is a rule that assigns every x value a unique y value. Now, this may sound confusing, but the example below hopefully will explain this. Whatever value I pick for x, I'm only going to get one possible answer for y. For example, if I plug in 2 for x, the only answer I could possibly get is 5. Now, if I did the opposite, if I plugged in 5 for y, I could possibly get 2 answers for x, 2 or negative 2. So the definition of a unique value for y is only getting one possible answer when you plug in a value of x. Now, we describe functions in many different ways. Function notation is another way of writing a function. We say it as f of x. Example below, f of x equals x squared plus 1. We use this in more non-graphical situations. It helps us when we want to plug in values for x. We can plug the number in for x in the parentheses, and that tells us what we're going to plug in x in the function. You can think of it as f of x and y are the same thing. The next concept, which is a challenging concept for many people, is that concept of domain. Domain is all the x values. Another way the book describes it is independent variable. Again, that's x values. When you look at a graph, x values, I start at the left and work my way to the right, and I'm talking about all the possible x values in a function. Domain and also range that goes with it is the y values. When I look at y values on a graph, I start from the bottom and work my way up. Y values are also called dependent variables because they are dependent on what the x values are. On the next slide, I do have an example of a graph, and we can talk about the domain and range. Here's a graph of a quadratic function. As you can see, I have listed the domain to be from negative infinity to infinity, which basically means any x value I pick is in this function. If I pick negative 5, there is going to be a y value corresponding with that. If I pick x equals 10, there will be a corresponding value with that. As you can see, the arrows going all the way to the left and all the way to the right would describe my domain. Range is described as starting at 0 and going to infinity. I start at the bottom at 0. That's the lowest y value that I have is 0. And I can go all the way up to infinity, 3, 4, 5, 6, and all the way up. I'll have x values to go with it. I do not have any y values below 0. As you can see, there's nothing below 0. Graphing a function, which we have all done with our calculators. Example here, y equals x to the third plus 2x minus 7 is a cubic function, which is going to give me something that looks like this. Not the most accurate picture, but you get the idea. The next thing they talk about is it a function or not a function, using the vertical line test. If you look at a graph, and you could draw a line vertically through it like my one in red, and if it crosses more than once, it is not a function. For example, this line crosses it 3 times. I could draw another line like this, and it would cross again 3 times. This is not a function. The one above, if I drew in vertical lines, anywhere I looked at, I'm only going to hit this graph once, no matter where my vertical line is at. So the one above is a function, the one below is not a function. I've giving you an example here of x equals y squared plus 9. Y squared is a good indication that this is not a function. If I solve for y, what I end up having here is plus or minus the square root of x minus 9. And as you can see, I get two functions, and I could graph them separately and be functions, but not together. The last concept that we're going to talk about here is continuity. I have continuity is basically, is a function continuous? Continuous means that if I'm going to draw the function, I'm not going to be able to lift my pencil from left to right. If I drew this one on the graph, if I started down here and I draw it, I am never going to lift my pencil off the paper. That would be a continuous function. Not all functions are continuous. The next few slides describe some examples of functions that are not continuous. The first one is what is called a removable discontinuity. The main thing you can look for is the domain going to equal 0? X plus 1 equals 0. If I set that and solve, x equals negative 1, that is going to be a problem. It is a removable discontinuity because if I factor the top, x plus 2 times x plus 1, the x plus 1 and the x plus 1, these would cancel out. So you would have a linear line x plus 2. But there would be a hole at that. If you graph this in your calculator and look at the table or zoom in at negative 1, you will notice that there is a hole in your graph. These are very often misleading because they do look linear, but they do have a discontinuity at where the denominator equals 0. Another example of discontinuity is a jump discontinuity. These are really easy to see because they look like step functions or piecewise functions. The example I have on the graph here is what's called the integer function. Integer function is an example of a step function where it'll start at negative 1, then it'll jump up to positive 1, then it'll jump up to positive 2, and you'll see these spaces in between the function. The last one that I want to talk about is called an infinite discontinuity. Again, graphically, these are very easy to see. You'll see graphs that'll zoom up to the top, or they'll zoom down to the bottom, and they will not, in this case, cross the y-axis. They will have what are called vertical asymptotes, which we'll get into in part 2. But in your homework, you'll be graphing these and being able to look and see what kind of discontinuity they have. Your homework for tomorrow will be page 98, 2 through 24, even. Again, you do not have to do this now. Save it for in class, and we will discuss this as a group tomorrow.